Right, well, good evening, everyone. And it's just heartwarming for me to see people coming out on a bank holiday Saturday to hear about physics. I think it's absolutely wonderful. So I'll try not to disappoint you. Yes, I am Professor Chris White, and the title of my talk is How Physics Connects Our Universe. I thought the best illustration of that would be a magnet trying to talk to a black hole. And indeed, there's a serious point in there that I want to come back to later on in the talk. So let me give you the basic idea of everything that I want to tell you this evening. And that's that our theories of the universe are just much more closely related than we previously thought. All of the theories we know about of physics. Now, that has practical applications, which I'll try and convince you of, but it might also revolutionize our understanding of nature. And I'm really excited about this research that I've been doing for about 10 years now or so. So if I want to talk about how all of our theories are related, I am going to have to give you a crash course in all of physics. So I've set myself that task, and may regret it, but I'll do it anyway. I then want to describe a new relationship. So it's about 10 years old now, but that counts as new, I think, in science. It's called the double copy, and it relates all of the old theories that we have with each other. And it also relates them to very, very strange new theories where we don't quite know what the point of them is yet. So these strange theories are appearing, and it's like there's some big structure that we're just about to uncover. And then I think this does have applications in physics and astronomy, so I'll try and convince you of what those are. Right, so let's have a slide then on why we should do physics in the first place, why someone like me chose to become a physicist. I would say I think that our species, humans, are rather remarkable. We just have this innate curiosity to understand the world around us. Now, sometimes that's for the reason of trying to enhance our lives, and we've done that over the last few thousand years. We've got amazing technology that's being developed all the time. But for someone like me, I think that's not the main reason we do science. It usually starts just because we're driven by curiosity and by the very, very big questions that face our species, and indeed this species that I've chosen to illustrate it with here. So the first question I would ask, I guess, is what is the universe made of? If we want to understand the world, we have to answer that. I think the biggest question that got me into science is how did the universe get here, right? Why are we here? Why is there something rather than nothing, and so on? This particularly frightened cat on the right is wondering how the universe will end. No cause for panic in this audience. We're not going to be around to see it. But indeed, that question is now within the domain of science, right? That is something we can, in principle, try and answer. So yes, physics, I think, goes a very long way to answering these questions. Not the only way to look at these questions, but my favourite one. So if we want to understand the world around us, I'll start with an experiment that you can do, which is just to look around you and notice that there's stuff in this room, right? I think we can all agree on that. So if we want to understand the world around us, we're going to have to explain that stuff. And in everyday language, we've got loads of words for that stuff, right? Things like solid, liquid, and gas, which are rather scientific words. But we've also got things like chair or table or things, ceiling and things like this in this room. Types of material like metal or wood or plastic or whatever. All of that stuff, to a physicist, we always like to simplify things. We just call all of that matter, right? So matter is the stuff that fills the universe. Now, the other thing we notice if we kind of look at stuff is that there's something that makes that stuff do things. So I can do things like take this piece of matter, throw it up, and then, of course, fail to catch it because I'm a theoretical physicist. But there are clearly some things that are making that matter move, some kind of influences. So it can make things move if they're not moving. Those influences can make stuff stop if it's already moving, and it can make stuff stay still if that's what it somehow should be doing. So again, we have lots of words for that in everyday language. As physicists, we just use the word force, forces, right? Those are the influences that take matter and somehow get it to do interesting things. Now, that distinction then between matter and forces is possibly the most basic distinction I can make in all of physics. And indeed, in our current theories of the universe, that distinction is still very much there. So once we've understood the matter, and once we've understood the forces, then we've gone a very, very long way then to explaining the universe. So then if I want to tell you about the laws of physics, I could start talking about the everyday kinds of objects we see in this room, like the book I just threw up and so on. Everyday objects, meaning we can see them, they're not too small and they're not moving too fast, so they're getting away from us. Those obey a set of laws of physics called Newtonian Mechanics. Now, I will happily admit we live in a country where we tend to name a lot more after Newton than in some other countries, perhaps. But nevertheless, this theory is known as Newtonian Mechanics because I'm using that in a very precise sense, so as not to confuse it with things later on. So what is Newtonian Mechanics? I think it was probably the first time in history where a set of detailed mathematical equations were written down that told us how matter responds to forces, right? So if we know that there's a piece of matter there, and I know what forces are acting on that matter, I can literally solve some equations that will tell me how that matter will move. And that was a very important historical step in kind of combining matter and forces, showing they should be related, and allowing us to actually do things and predict things, and that's what science is. So that theory is by now hundreds of years old, first written down in the 1600s, I think, but it's still very, very widely applicable. For most of what we see in everyday life, that theory is perfectly fine. So it will describe things that are moving, like that plane there. It'll help us improve things that we want to move further, like the javelin in that picture there. Things that we don't want to move because we want them to stay up, like that bridge. Engineers will use Newtonian mechanics in designing bridges. And impressively, even things like the entire solar system is also described essentially by Newtonian mechanics. Now, we take for granted nowadays, I think, that our physical laws should describe such things. I think in Newton's day, it would have been enormously controversial to suggest that the bodies in the heavens obeyed the same laws as things on the earth. So that's a much more profound thing, perhaps, than we think about nowadays. But yes, that's a huge range of behavior that Newtonian mechanics can describe. Now, the only thing wrong with Newtonian mechanics is that it's not actually correct, but that is the only thing that's wrong with it. So I want to explain what the other laws of physics are, how we know we need them, and what vaguely they look like. And in order to do that, I'm going to have to tell you about the first force that was properly described. So I think the first force historically that we really understood, and it's wonderful to be talking about this at the Royal Institution because Faraday was a big figure here and did a lot of this work back in the day, and his equipment's downstairs. But the first force we properly understood was electromagnetism. What electromagnetism tells us is that matter is made of little particles, and those particles have something called electric charge. Now, you will be familiar with the effects of electric charge if you've ever got a static electric shock or something like this. That's due to these charged particles moving about and doing things. And there are two types of those charged particles. They can have what we call a positive charge or a negative charge. And then if I put two positive particles together, they move away from each other. If I put, again, two negatives, they would do the same. If I have unlike charges, so a positive and a negative, they would come together. So that tells us then that there is a force. If I have charged particles and I put them somewhere in the universe, they will create some sort of force that tells the other charged particles how they should be moving. What is that force made of, in a sense? Or what is our modern understanding of where that force comes from? I think our modern understanding of that is that charged particles create things called fields that fill all space. So electric charges, if you put them somewhere, will create something called an electric field. If it's moving, it'll also create something called a magnetic field. And that's what this diagram here is meant to represent. The arrows here tell you that at that point in space, there's something called a field, and that's the direction it's pointing in. And if you put another charged particle there, it'll follow the arrow and do something. So that's kind of where the force comes from. But that's all very abstract, isn't it? So what I wanted to do is show you that fields actually exist and that we can see them. So if we could have the visualizer on, please. I am a theoretical physicist. I've got an enormous amount of trepidation of even going near something as practical as this. I did do a rehearsal earlier and hope you get your money's worth. So yes, this is a magnet. And you'll have seen such things as children. These are iron filings. What are iron filings? For our purposes here, they are little metal sticks. And we have equations that describe the fields and how they're produced by stuff. And those same equations tell us that those little metal sticks want to line up with the direction of the field. So if this magnetic field is some sort of set of arrows saying where the field is and where it's pointing everywhere in space, those little metal sticks want to line up with those arrows. So we can literally see those arrows moving about. We can see the iron filings creating lines that kind of go from the North Pole to the South Pole and kind of bend round from the North Pole to the South Pole. So we can literally see, yes, there is a magnetic field. We can see it directly. And we know the direction of the field, so we know it has a direction, and so on. So that then is magnetic fields. And yeah, this is just a lot of fun, actually. I should do it more often. Okay, thanks. Let's go back to the slides. Okay, so yes, as for Newtonian mechanics, if we want to really predict what the field is, then I need some sort of equations that tell me if I have these charges and they're doing this, they're moving or they're staying still or whatever, I can work out precisely what the fields are, so what the electric and magnetic fields are. Now, we have equations that do that. They are known as the Maxwell equations, and what I've done here to make these plots, for example, is put them on a computer, put some charges there and get the computer to solve the equations and tell me what are the fields. So indeed, that works very well. Now, there's a particularly famous solution of Maxwell equations that we need to talk about. So by a solution of the equations, I mean some allowed configuration of electric and magnetic fields, right? We can think of the job of those equations to tell us which configurations of electric and magnetic fields are allowed in nature and which aren't. And one of the things that can happen, so one of the possible solutions, looks like this. So I've, again, got a computer to draw this, but that blue arrow there is the electric field, and it turns out for this particular thing that can happen, that the electric field is getting bigger and smaller, as we can see in that curve there. And then that green arrow is the magnetic field. So let's see if I can do this. The magnetic field is kind of getting bigger and smaller as the electric field is, and the whole thing is doing that. Now, the other thing I have to tell you, and I wasn't brave enough to try and animate this, but that whole configuration of fields is also moving along the direction of that arrow that's going to the right, as far as you're concerned. So that is a kind of wibbly-wobbly pattern of fields that is also moving. We have a word as physicists for wibbly-wobbly things that move. We call them waves. And you will have seen them, of course, in your sink or in the sea, or Mexican waves do the same thing, of course, in a football stadium. So there are wave-like solutions of Maxwell's equations. Historically, this was enormously important because that turned out to explain the nature of light. People had puzzled for centuries up to that point about what light is made of. Light is obviously there. It allows us to see stuff. We can do things with light and put it through prisms and things like this. So there was this big puzzle about what is light actually made of. The answer then is that light is made of electric and magnetic fields. That we have these wave-like patterns, and when they worked out the properties of them, they were exactly the right properties that corresponded to light. Now, if I talk about any wave, I can talk about the distance between the peaks. That's what we call the wavelength. And so I can think of different waves there, can't I, with different wavelengths. Turns out that's all the different colours of light. That's where they come from. It's the different possible wavelengths that you can have of the waves. Things you may have heard of like X-rays or microwaves, radio waves, and so on. Again, they are all just electromagnetic waves. So that was a really important thing. Why did it lead to the downfall of Newtonian mechanics? Well, the point is about these equations is if they tell you that the waves exist, they're also going to tell you their speed. So we could work out for the first time the speed of light and see whether it agreed with the measured speed, and it did. But those equations told us something more peculiar about the speed of light, which is that the speed of light turns out to be the same no matter how fast you're moving. And that you may or may not know, is in obvious contradiction to the laws of Newtonian mechanics. Now, you may be familiar with this effect from everyday life, but let's say I'm walking towards you at, say, 3 miles an hour, and you're walking towards me at 3 miles an hour, I'll effectively see you as moving faster, because I'm also moving towards you. You're familiar with that kind of effect. And it turns out you just add the speeds, and that comes out of Newton's equations and things, whatever. The speed of light being the same, no matter how fast you're moving, is a bit like you're shining a torch at me, and I walk towards you, but I won't see that light as moving any faster than if I wasn't moving. And that's just not how everyday life works. It's not how Newton's laws tell us how the world works, and that's how we knew they should be replaced. The replacement theory for Newtonian mechanics is called special relativity. It's a very, very weird theory. It has very strange consequences. So it's things like clocks can tick at different rates depending on how fast they're moving or you're moving. Lengths can also change. So if you want to look slimmer, walk past me close to the speed of light, and you'll achieve it. Difficult to do, and you'd probably lose weight anyway if you did that, but anyway. All of these effects, of course, are very strange, but they are seen in experiments. So this theory was very controversial in its day, largely because people just couldn't accept that a theory that had been there for hundreds of years was not correct. And it was the first time, really, that had happened. Also, the effects were so weird, people just didn't believe them. However, I think these effects are only weird because the definition of something that is not weird is what we see in everyday life. When we're born, our brains start taking in information about what we see around us, and our brains are entirely conditioned by our everyday experience. Anything that goes beyond that experience, by definition, is weird, because we don't see it in everyday life. So now I think we're very used to the fact in physics that occasionally we have to let the maths guide us because our everyday experience will fail. And then we build up a new intuition by working with the theory a lot and doing experiments and so on. Okay, so that's one place where Newtonian mechanics breaks down. There is another place where it breaks down, and that's when things get very small. So if I were to zoom in on a piece of matter, I would find that it was made of atoms. And an easy way to think about an atom, I've drawn a particular one here called hydrogen. But atoms have something right in the middle of them called a nucleus. And then they have particles going around the nucleus, orbiting it, called electrons. And hydrogen just happens to have one electron. In general, you'd have more and so on, but that's a basic atom I've drawn for you there. Now, if you plug that situation into the laws of Newtonian mechanics, and you combine it with electromagnetism, that predicts unambiguously that electron will want to spiral into the nucleus. So it turns out, and it's remarkably difficult to actually calculate this, but it is true, the electron wants to radiate away these electromagnetic waves, and then it kind of loses its energy and it spirals into the nucleus. So in very simple terms, atoms should collapse, and they shouldn't be here at all. Now you can work out, actually, how long it would take for all of your atoms, all the ones in the universe, in fact, to decay. It's much less than a microsecond or something like that. So we can all do that experiment, can't we? That's not true, right? Atoms do exist, and we're made of them. So that led to a radical overhaul of what I would call small physics in the early 20th century. The theory that came to replace the Newtonian picture is called quantum mechanics. Quantum mechanics could fill several lecture courses in itself, and indeed at universities like ours, it does. The basic ideas of quantum mechanics, though, the one I particularly want to mention, is why it's so shocking, I think, for people still. So, yes, quantum mechanics is a seriously weird theory. The one thing it says that I think should shock us all is that you can only calculate probabilities for things to happen in quantum mechanics. You can't predict what will definitely happen. Now, that goes against what our traditional definition of science was. I gave the case of the book. Now, fair enough, I threw it up poorly and I couldn't catch it properly, but I could have predicted where it went. And I could have predicted that would happen, right? If I know where the book is, and I know how fast it's moving, I know how fast I throw it, and so on, Newton's laws would tell me exactly where that book goes, right? That's what science used to be. In quantum mechanics, the situation is more like, if I have an experiment that I do, and I run the experiment, I will know what the possible outcomes are of that experiment, but I don't know which one is going to happen when I make a measurement. So I could do the experiment, let's say I can prepare that experiment identically and do it 1,000,000 times. I will be able to predict how often I see this outcome, how often I see this outcome, and so on. That's what I'm able to predict. But what happens in each case is completely random. I have no way of predicting that. Now, that seems to change, I think, our very definition of what science is. It also, I think, changes our concept of what reality is and our relationship with that reality. Because what's the universe doing then when we're not looking at it? Is it doing all the possibilities at once? Or those happening in different universes or whatever, these crazy ideas people come out with. So it's a very peculiar thing, and I think we as humans have never really understood quantum mechanics. If anyone tells you they understand it, they are lying, but possibly to themselves, so be nice to them. I would say philosophers are still arguing about what quantum mechanics means in very friendly terms. The remarkable thing, I think, is that hasn't actually stopped us using quantum mechanics to revolutionize our lives. All of chemistry is essentially quantum mechanical. New chemistry has come out of quantum mechanics. Biology, of course, feeds in from chemistry. Electronics is very quantum mechanical. Things like this are an intrinsically quantum mechanical device. You would never stumble across a device like this unless you knew the laws of quantum mechanics and could design it, right? So it's there in our everyday lives, whether we realize it or not. Okay, so I've given you an enormous amount of information, haven't I, in the last few minutes? Probably appropriate at this point that I try and summarize it. The basic ideas we've seen are that objects can be big or small. So I've drawn a rather silly plot here, but it does work, trust me. I've drawn whether objects are big or small on that kind of vertical axis. I could also talk about whether objects are fast or slow, meaning are they moving close to the speed of light or are they not? And the theories that I need to describe each of those regimes is for everyday objects that are pretty big but pretty slow. That's Newtonian mechanics. If they get faster towards the speed of light, I need to use special relativity, and so that theory must somehow become the other theory as I take the objects slower, and indeed that happens. If the objects go very small, I need quantum mechanics, but the wonderful thing about making that plot is that it tells us something's missing, doesn't it? It tells us there has to be another theory that's sitting in the lower right-hand corner that describes very small and very fast things. Now, I'm not talking about chipmunks. Those are still in Newtonian mechanics at the top. But I mean things, the size of an atom or less that are moving at close to the speed of light. Is that happening in the universe? Yes, probably as we speak. They're whizzing around the Large Hadron Collider at CERN. That's a particle accelerator. It literally takes small things and accelerates them to close to the speed of light. In the upper atmosphere right now, there are things called cosmic rays that are hitting the sort of upper atmosphere and cascading down these very small, very fast particles. So we absolutely need that theory to explain the universe. The other thing is that is the theory in the lower right corner that becomes all the other theories, right? So is there one kind of fundamental or proper theory going on? Yes, it's the thing in the lower right corner. So I have to tell you what that is. It has a wonderful name. It's called quantum field theory. So quantum field theory kind of unifies all that other physics, right, of quantum mechanics, special relativity, into one single theory. Now, quantum field theory, even I'll admit, right, I mean, it's a particularly intimidating theory, I think, when people first come across it. It intimidates me on a daily basis. I've been doing it for 20 years. I think one of the reasons it's cumbersome for people is that you have to learn all of that other physics first, right, before you can even tackle quantum field theory. And the mathematics of it, people just get blinded by the mathematics when they first encounter this thing, and it stops them seeing the basic ideas, I think, that are going on in it. I'm going to try and convey the basic idea to you, as far as I see it, of what a quantum field theory is. And so I want you to consider that electromagnetic field that we saw earlier. So I talked about an electric and a magnetic field, but we saw that those occurred together when they made a wave. So I'll call that the electromagnetic field. We saw that field was described by equations, and those happen to be called the Maxwell equations in this case. We saw that those equations had solutions that looked like waves, and that was important because that explained the nature of light. What happens in the quantum theory is that those waves are no longer completely smooth. So they're not going to look like that nice picture that I drew for you before. They actually come in little lumps, or quanta is the fancy word, hence the quanta in quantum mechanics. So you get these little lumps or packets or quanta of the wave. So if you were really looking at an electromagnetic wave coming towards you, you'd see a succession of these little lumps. Now, those, to all intents and purposes, behave like particles. So there are particles of light. Light is carried by particles. Another way of saying it is that the electromagnetic force is carried by these little particles, and they have a name. We call them photons, which is a word you may have heard of. So a photon is a particle of light. So this is the scheme, then, of how you make a quantum field theory. You take some field equations, in this case the Maxwell's equations, you find wave-like solutions of them, and then you turn those waves into little particles, in this case photons. Why am I drawing such attention to that scheme? Because it turns out that it is completely general. So what we now know in our theories is that all of the matter and all of the forces in nature have fields associated with them. So, we've heard of fields of force, and the electromagnetic field is a force field. The new thing when this came about was that matter as well is associated with a field. So there are many, many electrons in the universe. I mean, there's loads of them in each of you, for example. Where do all those electrons come from? There is one electron field filling the whole universe. That field has equations that describe it. In that case, it's called the Dirac equation. That equation turns out to have wave-like solutions. And therefore, to make it quantum, we can make those waves into little particles, and those are called electrons. So that's where all of the electrons in the universe actually come from, this one electron field. And that's a marvelous way of kind of unifying everything that's happening in the universe into these things called fields. So almost all things in nature, and we'll see what isn't in a minute, are these quantum field theories. Now, up to now, of course, I've talked about quantum field theory as a type of theory, really, rather than a particular one. To give you the particular quantum field theory that applies to our universe, I would have to give you a list of all the matter fields, all the matter particles, and a list of all the forces and so on. So I just won't bother doing that for reasons of time. But that theory is called the standard model of particle physics. So it's essentially a set of equations that tells us these are the fields that are there in nature, these are the forces and how they interact. So yes, it describes all matter and most of the forces we know about. So much for matter. That's kind of where it's sitting in our theories of the universe. What about the forces? Well, it turns out that all of the forces we know about in nature are consequences of four what we call fundamental forces. Now, that may seem a strange idea because in everyday life we see lots of different forces. I can push this book, and I can also, it's not falling through the table and things like this, and that might look like two different forces. However, what's happening in both of these cases is kind of the same. I have charged particles in my hand that are repelling the ones in the book when I do that. So that's electromagnetism. Likewise, the charged particles in the table are repelling the ones in the book, and that's electromagnetism again, right? Other forces in everyday life, like tension, say, when you pull a rope apart, you're trying to pull the atoms apart. Those atoms are made of charged particles. Electromagnetism wants them to go back together again, right? So almost all the forces we see actually are just electromagnetic. So that's why that one on the left is particularly important. There are two forces we don't see in everyday life as much, for good reason, because they're confined to the atomic nucleus. So I showed you a picture of an atom, a highly technical one, which I took ages to draw, but I showed you a picture of an atom earlier. It had this very small nucleus in the middle of it. There must be a force then, mustn't there, that kind of binds that nucleus together and makes it very tight and small. So that is very strong. It's the strongest force in nature that we know about. It's the strong nuclear force. Very imaginative name, but that's what it does. It binds the nucleus together. If you take a nucleus and you watch it for a while, invariably, if it's a big enough one, it'll kind of break apart into smaller nuclei. That's what we call radioactive decay or nuclear decay. That's controlled by something called the weak nuclear force, because we know it can't be the other one. So again, we don't see that particularly often, but it is there. And then finally, a force, and we'll see why I've put it last in a moment, that we certainly know about from everyday life is gravity, right? That's obviously there. But then that's it, as far as our theories tell us. Those are the only four forces we know about. Now, when it comes to the first three forces, we know how to make those quantum and include the effects of relativity. So in other words, we have a quantum field theory of those first three forces. That is the standard model of particle physics, right? It's the description of all the matter in nature and how it interacts with three of the four forces. Now, the natural question then is, what about the other one? Gravity is actually much trickier to find out about, and that's not helped by the fact that it is so weak. So it's very difficult for us to do experiments, actually, that probe the nature of gravity. Now, it may puzzle, actually, some of you when I say that gravity is a weak force. I think in everyday life, we tend to think of gravity as a very strong force because we can't fly, right? We're bound to the surface of the Earth, and when we fall down, it hurts, and that's gravity. So we think of gravity as a very strong force. And I think there's even a part of me as a 44-year-old man that thinks if I just flap my arms hard enough, I will fly. No, not going to happen, right? So gravity is a very, very strong force. But let me remind you what's holding me on the Earth. It's the mass of the Earth somehow creating that gravitational force. So I've got the mass of the entire Earth keeping me on it. Now, the Earth's pretty big, isn't it, right? So some of you may have taken, I don't know, an hour or 2 hours to get here this evening. You went hardly any distance on the Earth when you think about it, right? The Earth is much, much bigger than that. It takes you a long time, even in a plane to go round the entire Earth. The Earth is also made of very heavy, blocky stuff, isn't it? Like rock and iron and seriously heavy stuff. So the mass of the Earth is something like, if it means anything to you, 10 to the 27 kilograms or something like this, right? Just a crazily big mass. And what am I leading up to? So I've got that mass of the entire Earth doing that, and I can do that, right? So I have overcome that gravitational field due to the entire mass of the Earth. Now, these aren't the strongest legs in the world, because I am a theoretical physicist for a living and not a professional high jumper or something like that. But that's enough to tell me that the forces that my legs are able to produce, which are electromagnetic in origin, are much, much stronger than the force of gravity. And indeed, if you work it out, it's something like 1 with 40 zeros after it. That's how much stronger electromagnetism is than the force of gravity. The other forces are stronger again, because they're holding the nucleus together, which is much smaller than the other stuff around it. So yes, gravity is very weak, and I'm sure that's related to why we're not quite able to put it in with the other forces, and I'll say more words about that now. But to begin that, I need to tell you what our best theory of gravity currently is, and that is a theory called general relativity. So this is the point at which I'd like to bring on the space-time continuum, which I'll talk about in a moment.
How are we doing with the space-time continuum? Is it safe?
It's holding together, I think,
Not very badly.
which is good. Right.
Okay.
So you may have heard the phrase general relativity before, and it was associated with Einstein, of course, and others who first came out with the theory in the early 20th century. The annoying thing, I think, about general relativity as a name is that there's nothing in that name that tells you it's a theory of gravity, right, at all. But it is, believe it or not, our current best theory of gravity. Like all the theories that go beyond everyday life, it's a bit weird. So it tells us that space and time can no longer be considered as separate things. We have to combine them mathematically into a 4-dimensional thing that we call space-time. So it's got both in there. And then we have to think of that space-time as stretching and curving like some kind of rubber sheet. So if you put mass into the universe, it kind of warps the fabric of space-time and creates this curved space. And that curved space turns out to create or to be the attractive force that we call gravity. Now, it's one analogy for that. And even professional physicists like me, yes, I work with the mathematics of the theory, but it's analogies like the things on the right that help me visualize it in my head. The thing on the right, I've drawn there a curved surface. So it's the surface of a ball. That is a curved surface. And imagine that I put 2 people at the points A and B on that ball, and I told them walk towards the North Pole, which I've marked N there. They would think that they're moving in a straight line, but actually they're getting closer together, so it looks like there's an attractive force between them. So that's some illustration of how a curved space can look like an attractive force. The rubber sheet analogy is good, because we can literally place a heavy mass onto the fabric of space-time, which it looks like is polyester. And then we can put other objects in that curved space-time and see what they do. And this did work earlier, please work now. Yeah. That small one is orbiting the larger one, right? That's what gravity does, right? It makes our planet go around the sun. So what the sun has done is it's warped the fabric of space-time, such that other things that go in it try to move in a straight line, but straight lines no longer exist. So they go in curved lines instead. And that kind of looks like the force of gravity that we see. So that picture is very useful. Let's put them both. It's just so much fun, isn't it? Let's put both on at the same time. Because they're having a race, aren't they? If you are a gambler, get your wallets out now. But yeah, okay, blue one's got there first. I don't quite trust leaving that there, but that's great. Okay, great. That works. So yes, that's what general relativity tells us the kind of force of gravity is. So what I'm going to need then, like all the other theories that we have in nature, is I'm going to need some equations, aren't I, that say mass cause curvature, right? And I'm going to have to know how to describe that and do things with it and so on. Those equations exist, of course. They're called the Einstein equations, after Einstein who first came out with them. What do solutions of those equations represent? Well, if gravity is the structure of the fabric of space-time, it's absolutely brilliant. Solutions of the Einstein equations represent the entire universe and what it could be doing. Because they're solutions for the structure of space-time at all points in space and at all points in time, right? So that is why, nowadays, questions like, how did the universe get here? What is the beginning of the universe? How will the universe end? Those are in the domain of science, because general relativity, in principle, tells us the structure of the entire universe, right, at different times. So it's an absolutely remarkable theory. And yes, because it's a remarkable theory, it has some very exotic solutions. So one of the famous solutions of general relativity is something called the Big Bang. So one of the things that the universe could do, according to the equations of general relativity, is not have always been there or be infinitely old, but have started at some finite time in the past and then expanded outwards. And that's what we call the Big Bang. That's not an arbitrary idea. It literally comes from solving the equations of general relativity and comparing it to experiments. Now, I said that gravity was the curvature of space-time. This won't do it, because we saw that the other things just orbited around it. But I could conceive of putting an object there that was so heavy that nothing else could escape, even if it was traveling at the speed of light. So those regions of space exist. They're called black holes. And that's what a black hole is. It's a region of space where the curvature or the warping is so big that nothing can get away from that region of space. Another nice prediction, particularly relevant for recent experiments, is if we take not a rubber sheet like this, but imagine that I had two of you, for example, holding a rubber sheet between you, even without putting a mass on the sheet, if one of you were to flap one end, then what you would see is little ripples or waves going along the sheet. Now, that is a remarkably good analogy for a solution of general relativity, which is that there are ripples or waves in the fabric of space-time itself. Those are called gravitational waves, because the structure of space-time is gravity, according to that theory. And those gravitational waves have been discovered relatively recently. So yes, I think it's a really exciting time for general relativity. It's just over 100 years old now, but we're entering a new era of precision experiments. So direct evidence for black holes has been seen for the first time in the last few years. Gravitational waves were seen for the first time in 2014, and they open up an entirely new way of seeing the universe. Traditionally, astronomy has meant look at the light, or maybe other wavelengths of electromagnetic wave, that distant objects give you, and then see what that looks like, and you can work out what's happening. There are many things in the universe that don't give off any light at all. But anything necessarily gives off gravitational waves. So we're suddenly able to see a lot of things in the universe that we simply couldn't see before. They were invisible. So I think there's going to be massive advances in astronomy in the next few years now that we're able to detect gravitational waves. Now, of course, why did I become a physicist? I told you at the beginning, because I wanted to know what happened at the Big Bang. Unfortunately, the equations of general relativity break down at the Big Bang. Right at the Big Bang itself, those equations stop making sense. Other people want to know, including me, of course, what's in the middle of a black hole. We can't really visit a black hole, and even if we could, we wouldn't really want to, because it's a one-way ticket, let's face it, right? So you're never going to come back and tell other people what was inside the black hole. The equations of general relativity break down in the middle of a black hole, so they can't tell us either, actually, what's happening there. And that tells us that the theory of gravity is not complete, right? And that's annoying. So yes, what are the problems with general relativity? We've seen that it breaks down exactly where things get interesting. What do we think might solve that? Well, it's widely believed that a theory of quantum gravity is needed. I said all the other forces, we know how to include the effects of quantum mechanics. That's important for them. And we can make all the other forces in nature quantum by doing this thing I told you about, called quantum field theory, where we reinterpret the waves in each theory as being made of little particles. And you may say at that point, well, you've just told us, Chris, that there's things called gravitational waves. Surely you know how to make the theory quantum. You just take the waves and you make these little quantum particles out of them. And if we did that, we would call them gravitons, which is the word that we use in our research papers. Unfortunately, when you do that, when you can do the mathematics of that, but the theory gives you nonsense answers. It's very, very predictable nonsense, mathematically precise nonsense, that tells you why it's nonsense. But that doesn't help the fact that it is ultimately nonsense. So we need to do something extra to general relativity to get it to work. One of the things that could work is adding extra particles to the theory. Unfortunately, when you do that, the calculations become very, very difficult indeed. Now, I wanted to try and really convince you why research on quantum gravity was held up for 40 years by the fact that the equations are so difficult. So I'm going to break one of the golden rules of talks like this, which is don't show any equations. I do want to show you them. Because the best way of showing you how complicated quantum gravity is to put it in front of you. So yes, I'm about to turn this genteel evening out into a horror film. So let's start with another force first. So I talked about the strong force earlier in nature. I said all of the forces are quantum fields. They all have particles associated with them. So there is a particle, if you like, that carries the strong force, that is responsible for the strong force. That imaginatively is called the gluon, literally because it glues the nucleus together. That's where the name came from. So the gluon carries the nuclear strong force. We're very interested in the theory of gluons. We want to calculate lots of things in it. Why? Because particle accelerators like the Large Hadron Collider collide particles called protons that to a large extent are made of gluons. Right? So we're not going to understand what comes out of those experiments unless we can very, very precisely calculate the quantum properties of gluons. And indeed, that's what I spent the last 20 years or so doing, is developing methods to get answers out of the theory of gluons. So yes, what's a typical question we might ask in that theory? It's a quantum theory, so we can only predict probabilities, but we might ask a question like, if I have two gluons coming together and they make a third one, what's the probability for that to happen, right? And that's directly related, that question, to the things we actually measure at particle accelerators. So the relevant formula for three gluons, again, what is the chance that those three gluons do something interesting, happens to look like this. I don't want you to understand at all what the symbols mean. It would take me about 4 years to explain them to you, which is the length of a master's degree. But what we can see is that I've been able to write them down for you, right? They fit on a slide, and they fit on a single line of a slide, right? And if I were to print this out, not many trees would be harmed, right? So we can count the symbols. There are not too many of them. Let me show you the corresponding result for gravity. Now, what is the question in that case? I have two gravitons that come together, and they make a third graviton. What's the probability for that to happen? So this is the kind of thing that happens. Now, I've taken this out of a famous 1960s research paper, one of my favorite papers of all time, actually, by Breistavit. He used this very sneaky notation, which it would take me about 4 years and 1 week to explain to you, to hide the fact that there's over 170 separate terms when you expand that thing out. Now, I'm going to ask all of you a question now. I'm going to give you an exam because I am a lecturer. Who thinks that is more complicated than that? Now, before you answer, I know what it's like when you come to things like this. You think, oh, he's saying what seems to be an obvious question, but there's a trick or something or whatever. No, this is not a trick question. Who thinks this is more complicated than this? Good. You're all experts on quantum gravity, which you may not have thought before you came this evening, but you're an expert in the main point of quantum gravity, which it's an absolute pain in the you-know-what. So this literally held back computations in quantum gravity for about 40 years. This was a question about what happens when three gravitons come together. We need many more than that for realistic calculations. So the algebra literally balloons so quickly that no human can do it. Nowadays, we would put things on computers or supercomputers, clusters, GPUs, whatever high-performance computing you have in your closet, but those aren't going to cope either, right? So we just weren't able to do the calculations in gravity for many, many years. Everything changed, however, in about 2010. So these three people here, who were in California at the time, found something quite remarkable. And they said, well, if you write the formula for any number of particles coming together in the right way, you get an almost identical result for gluons as you do for gravitons. Now remember, calculating gluons is much, much easier. And what they said is if you write that formula in a gluon theory in the right way, you can just tweak it a little bit and it automatically becomes a gravity formula. Why is that so important? We no longer have to do the big complicated thing that we used to do in gravity, because what happens when that algebra balloons is it sort of gets bigger and bigger and bigger and bigger, and then what we now know happens is that right at the end, it goes whoosh and becomes something much, much simpler. Now that tells you you were calculating it the wrong way. There's something else we can do now, take an easier theory, and then copy the results across to get the other theory. Now again, I mean, I've worked on this for 10 years. I can not show you the formulae, and I'm doing it for a reason. I don't want you to know what the formulae mean, because I think it's easier if you don't. I would like you to look at these formulae as pictures. So one of them is the formula for any number of gluons come together, what's the chance that that happens? The other one is for gravitons. Let's play spot the difference, right, as pictures. What I hope you see is that those formulae are basically identical. Can anyone see where the differences are? Yes.
Yeah, there's one that's different.
Yeah. So is it the thing I've called C at the top and it becomes an N at the bottom? Okay, so that's one. Anyone see another difference? Yeah, exactly. So there's something out the front called G in one theory, and then it's called kappa over 2 or something in the other theory. But that's it. You know, if you knew nothing about the formulae, you would say they're basically the same. That looks like the same theory. No, different theories. But we can write a formula in one and turn it into a formula in another. Now, another good way good thing that comes out of showing you the formula is that the name of this correspondence is called the double copy. It's only when you look at the formulae, really, that you can see why. If you look at the top formula closely, we took away this thing called C, as you pointed out up there, but we put an extra copy of the thing called N. So that thing already existed, actually, in the formula above. We just put 2 copies of it. And that's where the name double copy comes from. What it means is we're now able to find things out in gravity that were impossible before. We calculate them for gluons, and we recycle the results for gravity. So one of the first uses of this was seeing whether certain possible theories of quantum gravity might be well behaved after all, and indeed they're better behaved than we thought. So it's kind of revolutionized that study of quantum gravity. Now, where does this thing actually come from? There's not yet a proof of the double copy, so it is a conjecture, but that never worries physicists. You know, we've tested it, and it seemed to be correct in everything we've looked at. We can, however, get an approximate justification for it from something called string theory. Again, string theory would fill a whole series of talks in itself. That is a theory we know how to write down. What does it say? It says, well, all of the particles that are there in nature, imagine if you zoomed in on them very, very, very precisely, you would find that rather than being little tiny particles, they were actually little sort of bits of a string-like substance. And if you can have fields filling the universe, why not have these strings filling the universe, right? It's no different, really. And now there are 2 types of string you might think about. You could have a string with 2 endpoints, or you could have a string with no endpoints, what we call a closed string. And we know how to write down a relativistic quantum mechanical theory of strings. It turns out, rather crazily, that if you look at that theory and it's very high energies where that theory would apply, if you go to low energies, open strings turn out to look like gluons, closed strings turn out to look like gravitons. There are known relationships, due to these people here, between what open strings do and what closed strings do, and therefore there should be a relationship between what gluons do and what gravitons do. So that was actually the motivation for looking for this thing. However, the double copy for particles goes a lot further than the double copy for strings does. So it doesn't really give us the full explanation of what this thing is trying to tell us. But it is, of course, a very interesting explanation. So how general is this thing, the double copy? So far I've talked about it as a useful way of calculating particle interactions, right? You know, we can take this particular thing we want to calculate it in one theory and turn it into that particular thing in another theory. What first got me interested in this is that I'd like to believe it goes a lot further than that. And I'd like to believe this thing is really telling us that the theory of gluons and the theory of gravity are somehow ultimately deeply related to each other. And if that's true, then we ought to be able to take anything in the theory of gluons and turn it into things in the gravity theory. So the question I and others first asked was, can we take something in the theory of gluons, which it turns out looks just like electromagnetism in this case, can we take something in the theory of gluons and turn it into a black hole in gravity? Because black holes are cool, we like playing with them. And is it really true that you get a new way of thinking about black holes because you can do something in this theory over here and double copy it to make a black hole? And it turns out that the answer to that is yes. We know how to sort of think about black holes in expanding universes as related to a theory of gluons or electromagnetism, which is just much easier to think about. Now, the plot I've put here is the technical version of the picture that I showed right on the first slide. What I've done here is I've taken a particular object, it's like a rotating disk of charged particles in the theory of electromagnetism, and I've plotted its magnetic field. If we zoom out from that magnetic field, that actually looks like the field of a bar magnet. So it looks very, very like the configuration of iron filings that thing gave me over there. Now, little did I know, when I played with these things as a child, that I was secretly playing with rotating black holes, right? The mathematical properties of that are precisely related in a way that we can now write down to what black holes are doing. There's lots of open problems and mysteries about black holes, aren't there? So thinking about these, which we understand, might help us solve those thorny issues about black holes. What's another major practical use of the double copy? So I said that gravitational waves have recently been discovered. A major initiative around the world, I mean, there are probably hundreds of physicists working on this actually, is just can we do the calculations for how gravitational waves are produced? Because we need to know that because of the experiments, right? We need to know what have we seen in our experiment. So we need to know the calculations that go into, if I have these objects colliding, what gravitational waves do they produce? Now, those are very, very difficult calculations. What kinds of things do produce gravitational waves? Well, we saw that you need the entire mass of the Earth to hold me down on it. To get gravitational waves that you can actually see on the Earth, you need to basically think of the most violent thing you can think of anywhere in the universe, which is take two black holes and whack them together, right? So there are black holes in the universe that are orbiting each other, getting closer and closer together. They whack into each other, which is what this picture is showing, and that creates these ripples in the fabric of space-time, which are gravitational waves, where because those events are so violent, we see those waves on the Earth, even though they've taken a long time to reach us. So that's the kind of events we're now able to see, things like colliding neutron stars, another big heavy thing, and so on. So yes, calculations using traditional methods for how those gravitational waves are produced were extremely difficult to do for the same reasons that the quantum gravity results were that I was talking about before. The algebra just gets ridiculously complicated very, very quickly. What we're now able to do is take results, pretend that it's not black holes colliding, but gluons colliding, calculating that theory, and then copy it across to get the gravity result. And that has really reinvigorated the community of people working on gravitational waves. We already have results obtained with that method that just weren't possible by other methods. Those results are relevant for current experiments. The last thing perhaps I want to say before concluding is that all I've really talked about in this talk is the theory of gluons and the theory of gravity, and those being related by this thing called the double copy. It doesn't, in fact, stop there. So recent research has shown us that there are many, many other quantum field theories that are related by things like the double copy. So there's a complex web of quantum field theories, all related by mysterious correspondences. This is a plot I've happily stolen from a recent review article by J.J. Carrasco. Every blob on this diagram is a separate quantum field theory. Some of them are string theories, actually. So there's a mixture of weird exotic theories there. I doubt you can read the words in the blobs, but I don't understand them either, if that reassures you. Some of these theories are so weird. I don't know why people study them, but they sort of crop up and people say, oh, that's interesting, and they look at it. Every line on that diagram is a relationship like the double copy that turns something in one of those theories into something in one of the others, right? So there's this intricate web of precise mathematical correspondences that relate these theories. Now, if you're anything like me, you'll look at a picture like that and think, obviously there's some deep explanation behind all this that says why those theories are connected, right? And our traditional mathematical language for writing down the laws of physics, is the wrong one, because it's hidden this for decades, right? So it really does feel like we're on the cusp of discovering some deep underlying structure behind all of our theories of physics that we didn't know was there, and we're just getting hints of what's going on and so on. And I even think some of the mathematics that we need to understand this is probably related to open questions in pure mathematics. If anyone knows about algebraic geometry, well, first of all, if you do know about that, see me afterwards. But if anyone knows of a field called algebraic geometry, I think open problems in that are probably related to some of the new structures that we're uncovering in these other theories. So yes, almost perfectly to time, so I will conclude. What have I told you this evening? And thank you so much for coming out. Our universe is described by remarkably few ideas. Nevertheless, they are incomplete. The most basic theories underlying everything are quantum field theory, a particular one called the Standard Model of Particle Physics, and general relativity, which is our theory of gravity. Traditionally, these were very different things, but a new correspondence called the double copy tells us these theories are much more closely related than we previously thought. This has practical applications for astrophysics, depending, of course, on your definition of practical. It's practical as far as I'm concerned. This has practical applications for astrophysics, particularly for gravitational waves. And our fundamental theories, I think, may be completely rewritten in the near future. And with that entirely appropriate but ridiculous hyperbole, I shall end with a shameless plug. So if you want to find out more about this, I've recently written a book about it, kind of summarising the 10 years of research that I've been doing on this and the work of others. It's meant for a non-specialist audience, so if you enjoy this talk, that's the same level as the book. I also put chapters at the end of it on how to become a scientist. So I grew up in rather humble background, actually. I wasn't surrounded by people that had been to university, actually, let alone had become scientists. So I always thought if I became a scientist, if I wrote a popular science book, I would put in advice about how to become a scientist and what that looks like and so on. So I basically wrote the book I think I would have wanted when I was a teenager, even tips for confidence and things like this. And yes, thank you for indulging me. Thanks.